1 year after I had the long life dream of interviewing Milton Chang, I'm in the house of Michael Levy. In the house of Michael Levy to get to know him a little bit better. First, to know a bit of what it is to be the CEO of Lightwave Logic, to know a bit of what it is to be the person that is working a lot with European companies and with American companies and establishing lots of links in the photonic industry, and also to ask him for a few advices on what EPIC should be doing in order to be an international trade association, a worldwide trade association. Michael, thank you very much for this opportunity.
Oh, my pleasure. I'm happy to talk to you.
I would like to start with a little getting to know you a bit better. I already know you quite well, but I want the people also to get to know the part of Michael that I know. Who is Michael Levy?
Well, Michael Levy was born in London, educated in England, and then came to the States in 1985 and joined Bell Labs, AT&T Bell Labs, Bell, big telephone research center that did a lot of commercial, industrial-based research. And at the time, I was really interested in light. I always have been. And so light and semiconductors, well, we have photonics. And so my research at Bell Labs in the late 1980s was in photonics. And one of the things that I was particularly interested in is photonics integration, even back then.
1985, already photonic integration.
It was already happening. In fact, we didn't call it PICs. PIC is a shortened abbreviation for Photonic Integrated Circuit. At the time we called it OEIC, Optoelectronic Integrated Circuit, because we were thinking, how can we emulate the silicon IC in optics? And so we called it OEIC. I believe that name actually came from the Japanese, but the Americans used it at the time. And today we use Photonic Integrated Circuits, but it's the same thing. But I was interested in how you would put photonic devices together on the same chip and how would you miniaturize it. And so that was the subject of research. And there was a lot of very famous researchers at the time. One in particular, I think, one of the first OAICs was Bob Lahini. Dr. Lahini he finished as deputy director of DARPA, and he did some original work with lasers and laser drivers. You probably know Tom Koch, Professor Koch, Professor John Bowers, Larry Cauldron, all these folks were at Bell Labs at the time doing really cool integration work. And
which material was this? Was this gallium arsenide, indium phosphide, silicon?
Yes, so it was the 3-5 materials, because remember there was a telephone company, so the focus was on how can you make better emitters and detectors, laser sources and photodetectors that work with fiber optics. And clearly, long wavelength, 1310, 1550 nanometer solutions were of interest. Silicon Photonics, although we understood what Silicon Photonics wasn't really a subject at that time. But we knew about it, but silicon really was the focus for ICs, not really photonics then.
What was the reason for that? At the end, you wanted to integrate active material, light sources, or it was just an easier material to fabricate without having to involve the CMOS foundries?
It's a good question. I think the focus at the time was to get very high quality lasers to work down the fiber optics and photodetectors at the other end. And folks wanted to have high speed and very high reliability performance. And so obviously silicon doesn't laze, so the 3-5 materials were a natural choice. A lot of the researchers at the time were looking at waveguides and different properties of waveguides, both in glass, semiconductor, silicon, as well as polymers at the time. And so there was a lot of very interesting work. But I believe the AT&Ts really wanted the high performance lasers and photodetectors for the optical networks and the telephone networks.
And I guess when you wanted to reduce the size of the light source, when did the VCSELs come actually into play?
Well, I joined Bell Labs in 1985, and in the next corridor, Dr. Jack Jewell did the microresonator, and that was in 1989, and he got a gallium arsenide VCSEL at room temperature. And I believe it was sometime during the year of 1989. And it's one of those things where Bell Labs, where if there's a really good publication of research, everybody stops and looks at it. And that was one of those times. And Jack Jewell actually managed to get room temperature operation of a VCSEL. He called it a microresonator at the time, and everybody got excited. And then from that point on, many other researchers, both inside and outside of our labs, really took an interest in the VCSEL device.
All these VCSELs, vertical cavity surface emitting lasers, and now we see in the consumer electronics market. It's quite impressive, right? That finally, for me, this is the breakthrough of photonics in the last 50 years, when you have seen photonic devices really in mobile phones, like light sources, detectors that we are used to seeing the transceivers in the datacom market, see them fabricated for the large volume, high reliability. I drop the phone and the VCSEL doesn't break, doesn't even get damaged. That's a huge step. What do you think?
Well, it was interesting at the time because the vertical cavity device was really invented by Professor Iga in Japan back in the late 70s. And he had worked on that as a research topic, and he came over to our labs and developed his ideas. Jack Jewell also worked on a very early design. And you're absolutely right. Nobody really believed the VCSEL in the early 1990s was reliable. We had edge-emitting lasers that worked perfectly well. And so when I joined Motorola's research, corporate research in Phoenix in the end of 1989, my topic of choice was the VCSEL, because I saw what Jack Jewell had done and I thought, wow, this is a great area to be in. So we started doing research at Motorola in the VCSELs, and so did many others. The applications we were looking at the time were optical interconnects, short distance parallel optical interconnects. We never even imagined VCSELs would be used for laser mice in computers. We never even imagined you'd see VCSELs used for 3D sensing in iPhones. But you know, some of the work we did, like the first Oxide VCSEL the Motorola invented back in 1993, is the same type of VCSEL that's used in the iPhone today, when it sells hundreds of millions of units. And so as somebody who was one of the participants in that era, and there was plenty of others too, I mean, it's just great to see a technology progress from the research lab into very high volume consumer applications.
That's one of the things that I actually have learned from you, from some of your peers. It's not what you do, actually not even what you learn how to do, but it's also what you protect and what you actually tend to monetize or use in the future. And you have certain amount of patents. I think it's how many patents do you have?
Well, the US PTO patents, over 200. Maybe 215, 220.
Did you write all of those?
No, the lawyers actually write the patents. Typically, what an engineer would do is they write the technical specification of the invention, the idea, and you send that to the lawyers, and then the lawyers would write it in their own language in their draft, the spec and the claims, and then they go prosecute that with the examiners in Washington. So the attitude of Motorola at the time was, we don't really publish. So some companies decide they don't want to publish a lot of work. But what Motorola did want to do at the time was that we want to protect any inventions or ideas you have. And so they were very supportive. I think the number's over 400 if you look at the international derivatives. But here's the lesson. The lesson is not the number of patents you have or the ideas, because a lot of them were lasers and photodetectors and displays and different optical widgets and systems and modules. It's the process. Once you understand that a patent can protect your company, then you should take it seriously. You should try and get the right claims. You should try and work really hard with your lawyer to try and get the patent issued, because it's worth value, and that's important.
And you decided to patent the Oxide VCSEL. That was one of the patents that you have, right?
That's right. It's actually now expired because 1993. It's a long time ago. But yes, exactly.
And why? What did you see in the Oxide VCSEL to say, okay, there's money in here? It's a bottom DVR, it's a top DVR, I'm going to say it's not rocket science. It's a great idea, but it's not really rocket science. What do you think, this is something that I can patent, I can monetize in the future?
Well, the problems we were having at the VCSELs at the time were they were consuming a lot of current and a lot of power. And we were trying to find out ways to get the power down and control the current that goes from the top mirror to the bottom mirror. And we experimented with oxides, and it actually helped. And soon afterwards, many other people realized it was a really good solution for the VCSELs. And with reliability proven in the next few years, people began to implement VCSELs. And much to my surprise, there was a lot of negativity at first, but now everybody accepts them as being a very reliable laser device.
Indeed, oh, very, very reliable. And we are now in 1989, you started working with pixels with your colleague in the office next door. What happened afterwards?
Well, Motorola developed some products and then decided to get out of the photonics business. And so at that point, I moved to a number of different companies. One of the companies a lot of people were aware that I was at was Intel. And I was one of the people that worked with Mario Panicia to set up the Intel's Silicon Photonics group. And that was back in 1999 and 2000, where we had a big bubble in the telecom. Yes. And there was a lot of interest in how would you take Silicon Photonics, use the silicon mentality, the big fabs, to do photonics in a way that you could bring the cost down. Well, we knew we couldn't do the laser, but there's plenty of other waveguides and large spot converters and photodetectors, multipliers and demuxes that you could do. And that was the period where a lot of people became very interested in silicon photonics.
You know what, I finished my telecom engineer studies in 2000. It was the best time to find a job. That's why I decided to move to Bristol and do a PhD in quantum mechanics and quantum physics, because there was absolutely no job whatever in telecoms, which made actually a very good career path for me, because I learned to actually use photonics for other applications beyond that. How did you survive the telecom bubble? Tell me about those times.
Those were tough times, because a lot of companies went belly up, because a lot of the venture capitalists that were investing in the companies pulled their funds, and so it was difficult, because people were ready with technology to sell, and there was no markets. After that period, I realized that there was an opportunity in the US from the trade association standpoint. So one of the things you'll see from me is that I try and learn processes in depth, whether it's the patent process to protect IP or it's R&D for new devices. Different facets of photonics have always interested me. And in this case, I didn't really understand how Washington worked. Yeah. I didn't understand how trade associations worked. And so I went to work for OIDA in Washington, D.C., and as you know, eventually ran that organization. And that was a fun period, because it was bringing together the industry for common themes such as standards, such as roadmaps, such as forecasting, marketing, understanding where the markets were. And in general, what are the opportunities for photonics? And at that time, it was post-bubble. People were trying to figure out what was next. They had technologies from telecom and fiber optics that were developed with a lot of funding. And now they were looking for new opportunities, new applications.
They had plenty of solutions looking for problems.
Exactly.
And that was exciting times. Actually, I actually enjoyed that very, very much, because we really had all the technology that we developed for the datacom and telecom markets. We have fantastic low-cost 1.55 micrometer lasers. We had great detectors, and we had to find ways to actually monetize that. It was time to think away. It was the time in which you could actually have blue sky ideas bringing to the market.
I think we were very lucky in that period. That period was in the after 2000, in the 2000 to 2010 time range. And what we had was we had the results of 30 to 40 years of industrial R&D at IBM's TJ Watson labs, the HP labs, GE labs, Bell labs. We had those big industrial corporate R&D facilities that did a lot of photonics research. And that period was actually taking that technology and finding new applications. And now, as we move forward, we're seeing things like automotive, we're seeing things like biomedical, we're seeing sensing, we're seeing applications out and beyond just fiber optic communications. That's fantastic.
And very interesting, when you were in OIDA, you were running the association, and you had a large set of companies who were thinking, we invested like crazy in photonics in the last years. We really got in trouble because of that investment. Now we have the technology. We need to find ways in which we actually get some of the return on investment. And we are sitting here next to companies who are competitors and in exactly the same situation. How do you deal with that? when you are running an association and you have competing companies and you have to find ways in which they can actually help each other?
So I'll give you an example, because this is topical today. I mean, we're doing photonics roadmaps. I mean, AIM is doing it, Dynamic is doing it, Photon Delta is doing photonic roadmaps, and we did roadmaps at OIDA. But we didn't do product roadmaps. We did technology platform roadmaps. And so if you do technology platform roadmaps, then you're not really getting into the competitive products from each company. So you're keeping it at a fairly high level. What will the technology bring us in 10 years' time? Where will it go? What are the barriers? Very similar to what the silicon industry did with the ITRS roadmaps for the silicon red brick walls that everybody talks about. We did similar things at OIDA. We called them purple brick walls. Not quite the same, but for photonics, how far can we go? How low a power can we go? How fast can we go? What are the limits? And so what that did was it brought the competitive companies together, but in a way that these were common challenges.
What common challenges?
Common challenges like, how fast do you need to go for a telecom system? I mean, at that time it was, 2000 to 2010, we went from 1 to 10 gigabits per second in 2000, and then the challenge was well, customers really want to go 40. Well, lasers don't really go 40 gigabits per second, so maybe the easiest way to do this is gang 4 of them together and have a 4x10. So 2002, 2003, we started seeing transceiver modules 40 gigabits using 10 gigabits per channel. And by the end of that decade, the roadmaps were predicting, well, maybe the devices can go 25 gigabits per second as opposed to 10. So now we have 100 using 4 channels.
It's very interesting what you say about the roadmaps, but I can tell you one thing. I'm involved, I think right now, in at least 10 different roadmaps, and I keep having new roadmaps every year. Have you actually seen a roadmap that really reached the end of the road?
No, I haven't actually. And the interesting thing is that it's always easier to look back. So if we look back today for the roadmaps that we did 10 years ago, pretty much we've achieved everything. Now, we've done it in slightly different ways. For example, we're talking about, even at Photonics West and OFC coming up 400 gigabits per second. And we're looking at, 50 gigs channel, and we're using PAM4 modulation. 10 years ago, 400 gigs per second was on the roadmap, but we didn't know how to get there. We now figured a way to get there. And there's other ways to do that. And now, you look at the roadmaps today and you say, well, what's next? Well, it's 800, it's 1600 gigabits per second, it's 3200 gigabits per second. I'm not sure how to do that, but a lot of the technologists have ideas already and they're thinking about it. And so in 10 years' time, we'll look back and we'll say, wow, this is how we did it. So I don't see an end to it. I see the problems becoming more challenging. They require more investment, and that is a worry, the level of investment in photonics, because the faster we go, the more low power we go, the more miniaturization we go with photonics integration. It costs a lot of money for the hardware to be developed.
And one of the things that we are seeing is, especially in Europe, much of the innovation is done by very small companies, sometimes very young companies who really have very interesting ideas and make first development. Sometimes they really cannot even afford to patent, to protect those ideas, which is the first challenge. And second, to find the seed money for that. So do you see similar challenges here in America for the young companies to find this initial seed money for the development of their ideas?
Yes, I do. I mean, in 2000, I was at Intel doing corporate investment, and so we invested in these types of companies from an Intel perspective. Today, as you already have seen, many of the venture capitalists would like to invest in, 4 folks with a PC who can develop the new Instagram and sell the company for $1 billion. So the rate of return for that sort of scenario is almost infinite. When you have a little startup and you want to do hardware, it gets expensive to put a fab together or to order wafers and to order epi and do 50, 100 gigabits per second test equipment. That's really expensive. And so we have to be more creative in how we do that. So the first part of your question is it the same in America? Absolutely. Venture capitalists, more tend towards software because the better ROIs, the return on investment, than hardware projects. But that being said, I think it allows us to be more creative for hardware photonics companies that are looking at things like photonic integration. And certainly some of the things I've seen come out of Europe, like for example the pilot lines, they allow a lot of the cost to be shared, whether it's multi-purpose wafers or multi-purpose packaging, and so you're sharing the cost. Maybe there's a little bit more of a common platform, but it allows the SMEs, the startups, the small and medium-sized enterprises to have a chance without raising lots of money. And that's the secret. Can we set up a situation, an environment where small photonic companies can thrive without borrowing lots of money? And I think the answer is yes. And certainly from what I've seen in the European Commission's pilot lines as an example, that is one really good example where that's occurring. We've also seen that in the US with AIM Photonics, with the big Silicon Photonics play. So we're seeing countries take on that challenge.
But technology has no borders. At least this is my view. Technology has no borders. We should not be talking Europe or America. We should be talking at the joint development of photonic integrated circuits. So as you say, we are developing these pilot lines and we are trying to find ways in which the companies can benefit from this low barrier access. My dream is that EPIC provides a technology platform worldwide, that there is really no borders for that. Do you see a challenge for American companies actually saying, okay, I'm okay developing my technology and getting the photonics fabricated by European pilot line?
I think, as a person who's running a small company in the US, we are looking for opportunities. We want opportunities to partner. We want opportunities where we don't have to raise lots of money in order to get the technology complete. Now clearly, we have our own proprietary technology, but we also need to engage with the infrastructure. For example, when we're designing electro-optic polymer modulators, which is a modulator is a device that's been around a long time, and it's a fast optical switching device. Our differentiation is we're using polymers as opposed to indium phosphide or silicon photonics, and we know the natural ability of polymers allows it to be driven, operate very fast with very low power. And so just because we can come out with a very fast, very low power optical polymer modulator doesn't guarantee success. We need standards, we need roadmaps, we need the industry to support drivers, receiver chips, like the ICs that go with it. We need the packaging. How do you do 100 gigabit or more connectors? Even electrical connectors are a problem, let alone optical connections. And so trade associations such as EPIC can really add value in helping small companies, whether they're European based or they're US based, in helping the infrastructure understand, hey, we need to go faster, let's all do this together because we'll all get there and we'll all can benefit the customer base, whatever the customer base is, whether it's a big data center or a telephone exchange or it's LiDAR for cars, for automobiles, or even medical sensing. We need those opopportunities.
Let's put the example of Lightwave Logic. I'm really super excited about this company. You know that. You chose Polymer as your platform of choice. Why Polymer? Polymer is not a new platform for photonics. We've been using Polymer already for many years. Why now Polymer photonics?
Well, to tell you the truth, I didn't choose Polymer. Lightwave was around before I joined the company. Lightwave was originally a spin-out from DuPont. I think the founders used to work at DuPont, and they were polymer chemists. And they saw a way to make a much more stable, much more effective, high-performance electro-optic polymer. And they developed that over the years. And my job, with folks like Fred Leonberger, who's on the board, he used to be the CTO at JDSU, is to take this polymer technology and show its abilities in terms of high performance, low power. And you're absolutely right. 20 years ago, 25 years ago, I worked with polymers at Motorola because it was a really sort of a up and coming topical material, but it didn't make it. And it didn't make it because everybody at the time, and this is my belief, really focused on the telecom market. Because at the time, the obvious device was a telecom modulator. And the competition was lithium niobate. And the telephone companies, at least the buyers for these companies, had a choice between a lithium niobate modulator, which is crystalline, which is very reliable, very stable in temperature, or this new high-performance electro-optic polymer. And because there was concerns about the reliability, this is my belief, even though polymers with companies such as Gigabit Optics and BR Photonics, which are electro-optic polymer companies, they got Telcordia GR468 qualification, they still weren't able to penetrate the telecom market. And I believe that's more of a perception issue.
Yes.
I think the folks in the telecom industry that wanted a 10, 20-year lifetime said, you know, we're more comfortable with lithium niobate. We know polymers can operate much higher performance, but we're going to go with the safe routes. And today we're seeing solutions in Silicon Photonics, we're seeing solutions in indium phosphide, and what Lightwave is doing is solutions in electro-optic polymers. So I would agree, a lot of people I meet have worked with polymers before, and they said, why polymers again? It didn't work 20 years ago. But if you look at what the specifications and the requirements are by folks in the data communications and the telecommunications industry today, the performance of polymers is what people are looking for. They want very high speed, they want very low power, they want good temperature stability, but it doesn't need to be at the absolute maximum ranges that were expected 20 years ago.
And the fact that this is already a standard, mature technology that plays in your favor. At the end of the day, if it was something completely new, then you would say, okay, we have Silicon Photonics there, CMOS compatible, we have indium phosphide, who has been long traditionally be used in the electronics and now in photonics, so why polymer now when it's immature? But no, you say polymer has been used for 25 years and now it's fully mature, and we can actually use all the benefits that have been exploited for many other applications, can use them for the telecom market. And you share, and this is the key, you share many of the challenges with the platforms. For example, packaging. How are you dealing with the packaging of your photonic devices? Do you have your whole supply chain there, or is there something that, similar to other companies developing modules for telecom, they struggle with the packaging of their devices?
Packaging is an interesting discipline in that when speeds are low, you can design a package and you can design an optoelectronic device and you can put it in the package. As you increase the speeds towards microwave type levels, 50 gigabits per second, 100 gigabits per second and beyond, the package becomes part of the device design. So they must be integrated. You can't separate the two. And so when it comes to photonic integration and you want more than one device, then you really have to look at the package design as well as the device. And it's not just an optics problem, it's an electronics problem too. There's a lot of RF signals, there's a lot of electrical signals, the impedances that you really need to deal with. And so it becomes a tricky problem. And I don't believe as we move forward you can separate the package from the device. And so we have to come up with more innovative solutions to go do that.
Yet again, we're always arguing on the fact that maybe there are not enough standards for the packaging of photonic devices. So if we had a lot of standards, wouldn't that mean that we actually had to make the design of our chips that fit those standards?
I think that's certainly an opportunity. I think we're at the point now where classic packaging, gold boxes and things that we've used in telecom are now becoming expensive. We've got to be creative in how we redesign that. And yes, you're right, there's no real standards in packaging. I think that could help the industry. Certainly as you look across to the silicon industry, there's standards in packaging. And there's ways where you flip chip bump different types of ICs to circuit boards and things like that. And so I think we can learn a lot from the silicon industry, just like the Silicon Photonics has done in using some of the big fabs and the big wafers to get the costs down.
It's the time of acquisitions. I see acquisitions in photonic constantly now with II-VI acquiring Finisar, and we're going to see many of them in the coming years. Do you think that's good for the photonics community?
Well, it's interesting. A lot of people have said consolidation is needed in our industry. We have a lot of small players, and now we're seeing the consolidation. If you look at the industry in general, our gross margins and our net margins have never been that brilliant. And so we have the good companies with gross margins in the 30 to 40% range. I'd like to see them in the 50 to 60% range. And our net margins in the 5 to 10% range. I'd like to see that double. I'm hoping the consolidation will allow folks to really focus on making sure we're profitable. Because if we are profitable, then we can invest in the roadmaps and the next generation technologies, which we need to do.
Hey, definitely. And from Lightwave Logic perspective, you are focusing now on the 100G. Please correct me if I'm wrong, but the 100G modules is really like the sweet spot for Lightwave Logic, right?
So you're absolutely right. We're focused on the polymer modulator engines for the 100G opportunity.
Why 100G?
Why 100G? Well, everybody today is looking at 50G, and we have an optical device that goes faster. It's a natural ability through its velocity phase matching characteristics can go a lot faster. In fact, it probably can go even faster than 100. But let's just say 100 for the time being. And that's the next major node for the networks. Today, networks are, when you see aggregated numbers of 400 gigabits per second, it's based from the 30 to 40 gigahertz devices that can operate NRZ 10 on-off coding at 50 gigabits per second, or they can push it to 100 gigabaud if they're using PAM4 with extra levels, pulse amplitude modulation at 4 levels. If you can have a faster device, then you don't need as many lanes, you don't need 4 channels, and you don't need to go to the high levels of symbols per bit that people are using. And so we see the optical device, whether it's our polymer or whether it's indium phosphide or silicon photonics, that's the next node. And for that, we need standards, we need IC vendors to support it, we need packages, we need electrical connections to support it, electrical connectors. And so we need the whole infrastructure.
But you're serving the market demands not of today, you're serving the market demands of tomorrow. Do you see that as a big risk?
Well, we are doing the market demands today with our 50G modulator. But when you go into a customer say, okay, this is great, 50G modulator. What's next? What can you provide us on the roadmap that will support us in the next generation? And the next generation, I call it the next node, the next generation is 100G. I'm not sure what it is beyond that, but this is what the customers are looking for. They're certainly looking for devices today, and I agree with you as we see that in the show, Photonics West and OFC, but they're also looking for vendors to supply them the roadmap that's actually scalable. Scalable in increased performance and decreased cost. And it's that scalability the customers are looking for.
And can you achieve such scalability with your current company, or do you think you're going to have to go into contract manufacturing to achieve those volumes?
That's a very good question. I think our focus today is to make sure we can have the devices with the performance and the specifications the customers are looking for. And at that point, I think we can make a call whether we decide to do this ourselves, or if the volume is at a point where it makes sense to partner with contract manufacturing, we'll take a look at that too. And so we're open to how to grow the company, but I think let's take a step at a time. Let's show that we have not only the 50G, but we have the next node. And let's work with folks like EPIC, the trade associations, to help us create the next node. Because we can't do it all on our own. We need help from trade associations to do that.
So what can EPIC do for you?
Well, EPIC can put together workshops that deal with the issues of how do you get 100G being accepted by the community, and how do you get people to start working on it? EPIC can help with the standards for the packaging. EPIC can help with standards on the 100G issues there. It could certainly help with providing roadmaps to show folks where everything is going. And if the roadmaps have credibility, people will buy into it. And people look at the roadmap and go, wow, this is the same roadmap as what my customer is looking for. We should go do something about this. This is what EPIC can do.
And that's what I want to do at Epic. I want to bring all these companies together and have a setting in which they feel free to share what they want to share in a way that they don't feel the competition. But I can do this in Europe. I'm very happy that the Epic meetings work in a way that people feel super comfortable. I have to tell you the truth, I struggle to do this in America. Do you think there is a cultural difference between the European way of working and the American way of collaborating between companies?
Well, at the very highest level in Europe, a lot of companies do work closer together because that's how they do a lot of the projects. So you see a lot of companies work with universities, and the pilot lines, the photonic pilot lines, are one example of that. And that's been very, very successful. We've seen this begun with AIM, and I think it could actually increase more in this country. There are companies that do work together. We've seen things like COBO, the Consortium for Onboard Optics, where a lot of companies have been brought together for a theme of getting optics right to the center of the board as opposed to the faceplate. Could that be increased? I think it could. I think there's opportunities here to really push this even further. And I think also on the level of where you don't get into real product specifications, and then you can sort of avoid the competitive situation, and you can work on a platform saying, hey, let's try and solve a 10 kilometer, 40 kilometer, 100 kilometer type link. What's it going to be? Is it really going to be 1310, or is it going to be 1550? And really, what does the cost really look like that really applies to the application we're looking at? And I think this will happen, but I think it also needs encouragement too.
One of the things, another event they organized this year is about the automation for the packaging of photonic devices. And the idea there is to help companies, perhaps like Lightwave Logic, companies who are developing their own photonic devices, towards deciding whether to go to contract manufacturing or buying the machine from Polymer or from Fintech or Ficontech or Nanosystech and put it in their manufacturing center to do the packaging themselves, which is one of the biggest questions, when a company should actually do the contract manufacturing. And with this, and given the fact that for you, IP has been perhaps the most important part of the creation of a company, do you sometimes worry when you do the contract manufacturing on your chips on endangering your IP position?
It just depends on your business opportunity. Contract manufacturers have a very good place to play in the supply chain. They're very good at doing volume, they're very good at repeating things, they're very good at keeping the cost under control, and they're very good at bringing all the subcomponents together for a module, for example. And so it's a make versus buy decision by the company. Do you make it yourself, or do you buy it in from the outside? And each company will have their own make versus buy business decision to make. And as a company like Lightwave Logic, it just depends on what your customers are asking for, what their expectations are in terms of ramp and volume. It may well be, I mean, I've heard scenarios where if you really want to get into the data center market, you've got to be in a position to ramp extremely quickly. Yeah. And it may well be your business decision is you work with a contract manufacturer. Buying in these machines, they're good, great machines, but then the question you have to ask is, you don't want to buy in a machine and have it like sit around for 90% of the time. So you want to be able to utilize the machine well, and that comes in your make versus buy decision. So it may well be that some folks decide to buy in a machine and work with a contract manufacturer at the same time, or they may want to stage it. What I can say about Lightwave Logic is when the time comes, we will look at this, and we look at the make versus buy, and we'll make the right decisions for the business that we're looking at and the ramp we're looking at.
And that's why we organize these kind of events. And as I said before, for me, Epic is a technology platform. It's also a trade association, but it's a technology platform. I want people to have the help they need to make those decisions by talking to their peers. And that's why, for me, the idea is to have these events in Europe, but also bring those events also to the US, to China, to Japan, to all the areas where there is the need for this open discussion. I always believe in this open discussion.
Yeah, and I think you're right. I think there's wonderful opportunities on a global scale, especially with the international trade associations in optoelectronics and photonics. And certainly I think this country can benefit for those types of meetings. I've attended some of your workshops in Europe, and the thing that is really impressive about EPIC workshops, and they're usually designed for 50 to 100 people, is that the participants participate. And so a lot of the workshops that we ran at OIDA, it was part of my job to have the audience participate. And it's very difficult, and you've already seen that yourself, you stand on the stage and you can make 3 or 4 presentations and you bring in some great companies, but then you want that interaction with the audience. And that's difficult to do. And EPIC does a great job of audience participation. And when you get that, then these issues of whether it's coherent or direct detection or it's 1310 or it's 1550, these issues need to be discussed. These are not product-based issues. These are issues that affect everybody all the way up the value chain, from the material suppliers that do the epi on the wafers all the way up to the folks that who run the data centers and do the social media.
Let's talk now about something completely different. What is this that I'm looking at?
The background here are actually, believe it or believe it not, Legos. What these are each one is an individually designed house or hotel or supermarket. There's a barber shop. And so we put these together and we decided to display them. And I think there's probably like 15 different houses. So it's called The Street. And I came in one day and I had a text from my wife who said, "The people are falling over." And what actually happened is we had a mini earthquake and all the people in the front had all fallen over. And I didn't really understand what she was talking about.
Of course, because I cannot even imagine the amount of man hours that are in here, right?
It's a fun thing to do, to relax. And we enjoy that.
At the end of the day, I think most of the engineers, we have a passion for Legos because we like to build things. From the beginning, we really like to have some kind of assembly rules, of packaging rules, if you want, and being able to actually build something based on those very open rules. At the end of the day, designing a photonic integrated circuit, we're actually trying to bring the Lego mind that we have, right? To have building blocks for the modulator, for the laser, for the detector, and being able to put them together, following the very simple rules.
Exactly. I mean, Lego is a building block, and photonics, integrated photonics, are building blocks. And certainly, from some of the EPIC workshops I've seen, EPIC bring together different companies and universities to discuss the different building blocks. And it's a similar sort of approach, yeah.
Okay, so I know that you have another passion, which is the passion of owning different glasses. I've seen you in many different glasses.
So yes, I have a collection on the wall. We'll take a look in a second. There's about 200 different spectacles, different designs. And about 20 years ago, as you already know, I'm interested in optics, I'm interested in photonics, and I always have been. I realized I was wearing contact lenses all my life. I didn't really wear spectacles. And in about 1998, I got conjunctivitis in one of my eyes. And I just so happened to have 2 very old pairs of specs which I didn't wear. And so I went to work wearing one of those pairs of specs. And sort of people were looking like, "Oh, you're wearing a pair of specs today." So the following day, I changed the specs to my other pair. And I noticed folks look at me slightly differently. So I thought, well, this is interesting. So then that weekend, I came up to San Francisco and I bought half dozen pairs of avant-garde specs. And I thought, I wonder what would happen if I changed the style.
Yeah.
And so I did that, and I had a different reaction. Some specs were jovial, some were happy, some were serious, some looked like you were studious, and some looked like you were really in a grumpy mood. And once I realized this is like a prop for an actor on a stage. So then I started buying more extreme looking spectacles. And I met a couple of friends of mine who are members of antique spectacle societies. And they said, why don't you just buy some old specs, like sort of antiques, and then wear those? And that's what I did. And so my collection ranges from about 1760, when spectacles first had arms, and they look like the old round specs that Scrooge has in The Christmas Carol, to spectacles that are 100 years old, and spectacles that are 50 years old that were sort of stylish in the 50s and the 60s. And so the collection ranged with wearing different types of spectacles. And what is interesting is that depends on which pair of spectacles I wear, I'll get different reactions.
And you also know you have a third passion. So because you are an engineer, you have Legos. Because you love optics, you design and actually wear different pairs of glasses. And you are a telecom guy. And you also like to collect stamps, right?
Stamps is a new thing. I had an uncle who died in England about 3 years ago, and he bequeathed me his stamp collection. And it was interesting, when I was 8 years old, I used to collect stamps, as many children used to do at the time. But I couldn't keep it up because, if my father didn't buy the stamps, I couldn't really collect them. So after a couple of years, I sort of went on to different things. And then when he bequeathed me his collection, I remembered the collection from a childhood, and I decided to finish the collection. And his collection is to collect British stamps in the reign of Queen Elizabeth II. Unfortunately, he died when he was 91, and the Queen still lives. So I'm going to keep that collection going until the end of the Queen's reign. And it's a fun thing to do.
Michael, I really enjoyed this. I have to say that has been a fantastic 1 hour of my time. Thank you so much for this time, for all the knowledge that you have given me, for sharing your passion with us, and for being one of the stars of EPIC. Thank you so much.
Thank you very much.